Imagine your team just deployed, I don't know, like 50,000 lines of Python code to a production server.
Oh boy. Yeah, the classic deployment nightmare.
It is a critical application. You've got thousands of users relying on it. And the absolute second it goes live, the entire system just completely crashes, like total failure.
Total meltdown.
Yeah. And the culprit, buried deep, like deep down in the stack, a single function expected an integer, but another function accidentally handed it a string.
It is the ultimate developer nightmare, honestly. And the scary part is, it happens far more often than people think.
Really?
Oh yeah,
Yeah.
especially when code bases scale quickly. You lose track of what data is moving where.
Right. And, well, today we are looking at exactly how the pros keep that exact scenario from happening. So, welcome to this deep dive.
Glad to be here.
Now, since you, the listener, already know your way around basic Python, you've got your variables, your loops, conditionals, and object-oriented programming down. So we are skipping the beginner stuff today.
Yeah, we're definitely jumping into the deep end.
Exactly. We're using a really fascinating lecture from David J. Mullen at Harvard University. It's titled Introduction to Programming with Python, etc., and we're using that as our roadmap.
It's a great source.
It is. We want to figure out how to jump from writing code that, merely functions to writing code that is truly, like, Pythonic.
And I have to say that et cetera in the title,
Mm-hmm.
it is highly deceptive.
How so?
Well, I mean, in a lot of subjects, et cetera, kind of implies the leftovers, right? The stuff that didn't fit anywhere else.
Like the junk drawer.
Exactly, the junk drawer. But in Python, it represents the absolute secret sauce. It's the advanced tools, the stylistic decisions, and crucially, the safety measures that completely separate an amateur script from professional software engineering.
Okay, so let's get right into it. Let's start right at the intake valve, basically.
Mhm.
How we actually pass data into functions.
Good place to start.
Because when you first learn Python, you define a function and you give it exactly like 1, 2, or maybe 3 specific parameters.
Right,
maybe.
very rigid.
But advanced Python relies heavily on this concept called unpacking. And it uses 2 pieces of syntax that, honestly, they look incredibly strange the first time you see them. I'm talking about star args and double star chords.
Yeah, the asterisks. For anyone coming from an older language like C or something, seeing asterisks immediately triggers this deep fear of pointer arithmetic.
Oh, yeah. Pure panic.
But in Python, star args and double star quarks are brilliantly simple, actually. They basically allow a function to accept a completely variable, technically infinite number of arguments.
Infinite arguments. I always try to think of standard function arguments like packing and unpacking a suitcase, the tedious way.
Okay, how so?
Well, you open the bag, you take out a pair of socks, you walk over to the dresser, you put them away, then you go back to the bag for a shirt, walk to the closet, hang it up, one by one.
Very methodical, very slow.
Right. But unpacking with a star in Python, it's like unzipping the suitcase, turning it completely upside down, and just dumping the entire contents onto the bed all at once.
That is a great analogy. And, taking that analogy just one step further, Python is actually smart enough to route all those dumped items to the right places instantly.
Wait, automatically?
Yeah. So a single asterisk, star args, it unpacks a sequence, like a list or a tuple. It basically takes a collection of items and passes each one as a separate positional argument.
Okay. And the double asterisk.
Right, the double asterisk, quargs, that stands for keyword arguments. It unpacks a dictionary. So it's passing key value pairs as named arguments directly into the function's local scope.
So, okay, if I'm building like an API request function,
Yeah.
and I don't know if the user wants to pass in 2 configuration settings or maybe 20 of them, I just use double star quarks.
Exactly.
I don't have to hard code 20 optional parameters and just hope I guessed right.
Nope, it just catches whatever they throw at it.
That's wild. But what really drives this home for me is that you don't even need to look at an advanced API to see this at work, do you?
Not at all.
You can look at literally the very first function we all learn in Python, the print function.
It's the perfect example. I mean, most people use print by simply passing in one string, like print quote, hello world, end quote.
Right, that's day 1 stuff.
But if you actually look at the official Python standard library documentation, the actual signature for the print function is so much more complex.
It's surprisingly long.
It is. It's print, parenthesis, star objects, comma, sep equals quote, space quote, comma, end equals quote, slash end quote, comma, file equals sys.cout, comma, flush equals false.
I mean, why does a basic print function need all of that extra baggage?
Because it's designed for universal utility. That very first parameter, the star objects 1.
Yeah.
That is exactly why you can pass print one single string or, 5 different variables separated by commas. It takes whatever you throw at it, unpacks it all, and processes it.
Oh, I see. And then it uses those keyword arguments to format the output, like the sep parameter, which is
Yeah.
short for separator, right?
Exactly.
It defaults to a space. That's why if you print multiple words, they get automatically spaced out.
Right.
But if you're, say you're generating a CSV file from a script, you can just change sep to a comma, and instantly your output is perfectly comma separated.
It's that easy.
And the end parameter defaults to a new line, which makes sense. But you can change it to a space if you want a loop to just print on a single continuous line instead of dropping down every time.
Yeah, it really shows how Python hides immense complexity from beginners, but it leaves all that power highly accessible for experts when they need it.
That's fascinating.
Yeah.
But wait, I have to ask. If we can throw an infinite number of arguments into a function, I mean, that sounds incredibly freeing, sure, but also terrifying at scale.
It can be, yeah.
Which kind of circles us back to that 50,000 line crash we talked about at the very beginning of the deep dive.
The nightmare scenario.
Exactly. If things are this flexible, how do you keep a massive code base from just collapsing under its own weight?
Well, you have to transition your mindset. You go from a mindset of absolute flexibility to a mindset of controlled state and safety.
Oh yeah, controlled state.
And a really big part of that is managing your scope. For example, how you handle global variables.
Now, global variables are generally considered a massive code smell, right? I mean, if any function anywhere can just change a variable, tracking down a bug becomes nearly impossible.
Exactly. It's a debugging nightmare. But there are rare architectural cases where you explicitly need a function to modify a state variable that lives at the very top level of your program.
Okay, so what do you do?
Python forces you to use the global keyword inside the function to do this. It's essentially the language's way of making you sign a waiver.
A waiver.
Yeah, you are explicitly stating, I know I am reaching outside my local scope and I am taking full responsibility for whatever happens.
Don't blame Python when this breaks.
Pretty much.
Okay, but what if you have a value at the top level that should absolutely never change? Like, the value of pi, or maybe a specific server URL for your database? How do you lock that down?
Well, unlike some other languages, Python actually doesn't have a strict built-in mechanism to lock a variable in memory so it can't be mutated.
Wait, really? No constant keyword?
Nope. Instead, it relies entirely on community convention. You name the variable in all uppercase letters.
That's it, just caps lock.
That's it. It's basically a gentleman's agreement among developers. When you see an all uppercase variable, it means treat this as a constant. Do not write code that changes this.
Okay. I mean, I can respect the gentleman's agreement. I like the trust. But I'm going to heavily push back on this next safety measure from the source material, type hints.
Oh, I figured you might.
Because look, the absolute best part of Python, the reason it is so universally loved for rapid prototyping, is dynamic typing.
Is incredibly fast to write, yes.
Right. I don't have to declare that X is an integer and Y is a string, like I'm writing Java or C++ Grive. I just write X equals 5, and Python handles the memory allocation under the hood. Why on earth would we want to start adding strict types back into our code?
It's a very, very common pushback. And you're totally right that dynamic typing is incredible for speed and prototyping a quick idea.
Thank you.
But let's look at the reality of maintaining software over, say, 5 years. Imagine refactoring a core utility function in a massive dynamically typed code base.
Okay.
You change the function to return a list instead of a single string. In pure Python, you have absolutely no idea how many downstream services you just broke until you actually run the code and it fails.
Oof. Yeah, that's true.
Type hints were introduced to solve this exact problem.
So we're talking about the syntax where you define a function and you add a colon followed by int or maybe an arrow pointing to stri to indicate what it returns.
Precisely. If you look at Python's official typing documentation, it outlines exactly how you can specify what data a variable should hold. But, and this is the crucial part, Python actually remains dynamically typed at runtime.
Wait, what?
Yeah, the interpreter actually completely ignores those hints when it's executing the code.
Hold on. If the interpreter ignores them, how does that stop the 50,000 line crash? What's the point?
Because you don't rely on the runtime interpreter to check them. You use an external static analysis tool. And the absolute standard in the Python ecosystem for this is a tool called MyPy.
MyPy. Okay, so this is something you have to install separately.
Yes. You just run pip install MyPy in your terminal.
Okay.
And then before you ever deploy your code, or honestly even run it locally, you run MyPy against your files from the command line.
And what does it do?
It scans every single type hint. It traces the logic of your entire application, and it flags any inconsistencies. It will literally tell you, hey, on line 402, you are passing a string to a function that explicitly expects an integer. Yeah, it gives you the architectural safety of C++ or Java while letting you keep the runtime flexibility of Python.
It's basically like having a meticulous editor review your manuscript for plot holes before it ever goes to the publisher.
That's a perfect way to put it.
And speaking of manuscripts, writing the actual logic is apparently only half the job. If you want code to be professional, you really have to document it properly.
Absolutely. The code itself only tells the computer how to execute a series of operations.
Right.
But that doesn't help the human being who inherits your code base 6 months from now. They need to know what the code is supposed to do, and honestly, more importantly, why certain decisions were made in the first place.
And this is where docstrings come in.
Yeah.
For the listener, those are those triple-quoted blocks of text sitting right at the very top of a function or a class definition.
Exactly. And the community doesn't just leave this to personal preference either. There's a specific document, it's called PEP257, which serves as the gold standard style guide for exactly how docstrings should be formatted.
Oh, so there's actual rules for it.
Yeah, and if you follow these conventions, any modern IDE like VS Code or PyCharm will automatically pull your docstrings and display them as little tooltips when other developers are using your functions elsewhere in the code.
That is so cool. Okay, so our code is safe, it's statically checked with MyPy, and it's documented beautifully using PP25 and 7. But how do we make it truly elegant? Because, writing out a 5-line for loop just to double the numbers in a list, it still feels kind of clunky, even if it's well documented.
Yeah, it does. And this is where we cross over into the territory of functional elegance. A traditional for loop is what we call imperative.
Imperative, meaning what exactly?
Meaning you are micromanaging the computer. You tell it, okay, create an empty list. Now look at the first item in the old list, multiply it by 2, append it to the new list, move to the next item.
It's exhausting just listening to it.
Right.
It's like using a restaurant analogy. An imperative loop is like walking into the kitchen and giving the chef a 10-step recipe. Grab a bowl, crack an egg, whisk the egg, turn on the stove.
Exactly. Functional programming, on the other hand, takes a declarative approach. You don't tell the system every single step, you just declare the transformation you want.
So staying with the restaurant, it's like you just sit at the table and declare, give me a list of all the even numbers on the menu.
Beautifully analogous, yes. In Python, you can achieve this with built-in functions like map and filter.
I've seen those.
Yeah, map takes a function and applies it to every single item in an iterable automatically. And filter takes a function that evaluates to true or false and extracts only the items that return true.
Okay, but the most famously Pythonic way to handle this isn't map or filter, is it? It's through comprehensions.
Yes, list comprehensions and dictionary comprehensions.
The mental model for a comprehension is fascinating to me because it almost flips a traditional loop completely inside out.
It does.
Instead of the result being buried inside the loop, a comprehension puts the result first. So you write bracket x times 2 for x in my list. If x is greater than 10, bracket.
Which is incredibly elegant.
It reads exactly like an English sentence. Give me x times 2 for every x in my list, but only if x is greater than 10.
It condenses the creation, the transformation, and the filtering of data into a single, highly optimized, incredibly readable line.
It's amazing.
And while we're on the subject of optimizing traditional loops, we absolutely have to talk about enumerate.
Yes.
Yeah.
Because in a standard for loop, you frequently run into this really annoying problem. You are iterating through a list, but you also need to know the index, like the exact position of the item you're currently looking at.
Right.
And the amateur way to solve this is creating this manual counter variable outside the loop, setting it to 0, and then manually adding 1 to it at the very bottom of the loop.
Which is tedious, and it introduces a very high risk of off-by-1 errors.
Totally.
The enumerate function solves this perfectly. You just wrap your list in enumerate, and as the loop runs, it simultaneously yields both the index and the item. And a great little detail is that it accepts a start parameter. It defaults to counting from 0, as computers naturally do, but you can easily tell its start equals 1 if you are, say, generating a human-readable numbered list.
That's a great tip. Okay, so we are transforming data cleanly, elegantly. But what happens when the bottleneck isn't the speed of your loop, but the actual physical limits of your machine?
Memory management.
Yeah, because if I feed a billion rows of data into a list comprehension, I don't care how elegant the code is, my laptop is still going to freeze and crash because it just runs out of RAM.
That is the hard limit of working with lists. A list data structure holds every single item in your computer's RAM simultaneously. If the dataset exceeds your RAM, the program dies. Simple as that.
So to handle massive scale, we have to rethink how data is accessed entirely.
Yes, but let's actually tackle uniqueness and lookups first before we get to the absolute memory limits.
Okay, sure. So what if I have a data set of, let's say, 10 million email addresses, and I just need to know if there are any duplicates? Or maybe I need to check if one specific email exists in that massive pile. Searching through a list one by one is painfully slow.
Painfully slow, so instead you convert it into a set. A set is a built-in Python data type, and it's based on mathematical set theory.
Okay, and what does it do?
Its core characteristic is that it absolutely guarantees uniqueness. If you pass a list with duplicate emails into a set, the duplicates instantly vanish. They're just gone.
Wow, just like that.
Just like that.
Right.
Furthermore, because sets use a mechanism called hashing under the hood, checking if an item exists in a set is almost instantaneous. It doesn't matter how large the set is.
That handles speed and uniqueness perfectly then. But going back to the sheer size of the data, how do we process 10 billion records without just melting our RAM? The core material here dives into iterators and generators.
Right. So a generator solves the memory crisis through something called lazy evaluation.
Lazy evaluation.
Yeah. Instead of computing all 10 billion items and loading them into RAM all at once, a generator computes and produces one single item at a time, exclusively when you ask for it.
It's exactly the difference between downloading a 4K movie versus streaming it live on Netflix.
Oh, that's a brilliant way to look at it.
Right, because a list is like downloading the entire 100 GB movie file to your hard drive before you can even press play. It demands massive storage up front.
Exactly.
But a generator is like streaming. You only load the few frames of video you are actively watching into memory at any given millisecond, and once they play, you just discard them to make room for the next frames. You could theoretically watch an infinite stream without ever running out of hard drive space.
That is the exact mechanism of action. And the magic word that turns a normal Python function into one of these streaming generators is yield.
Yield. Because normally, when a function hits a return statement, it spits out the final answer, and then the function effectively dies.
Right. It's done.
The local variables are destroyed, the memory is cleared, the execution is just over.
Exactly. But yield behaves completely differently. When a function hits a yield statement, it spits out the value, sure, but then it freezes.
It freezes.
Yes, it preserves all of its local variables, its current state, and its exact position in the code. It basically just goes to sleep.
Oh, wow.
And then the next time the program asks the generator for a value, the function wakes back up, picks up precisely where it left off, computes the next iteration, and yields again.
That is a staggering amount of power for processing big data. I mean, you could parse terabytes of server logs line by line on a basic cheap laptop using a generator.
You really could. It fundamentally changes what your hardware is actually capable of.
Right, so the engine is completely built. We have a program that uses quargs for flexible inputs. It's locked down with type hints. It's checked by MyRPI. It's elegantly written with comprehensions. And it processes infinite data streams using generators.
It's a masterpiece.
It is. But right now, it's still just a Python file sitting on my hard drive. If I want to actually use this as a tool, if I want to run it from my terminal and pass it a file name, I really don't want to have to open the source code and hard code the file path every single time.
No professional developer does that. You need to package your logic with a professional command line interface. And in Python, the standard library tool for this is called argparse.
Argparse. So it basically acts as the bridge between the raw terminal and your actual Python logic.
Exactly. Argparse automatically parses the text the user types into the command prompt. It routes those inputs into your variables, and it handles errors really gracefully.
So if a user runs your script but they forget a required argument,
Argparse stops the execution and automatically prints out a really helpful error message. It even auto-generates a -- help flag so anyone can see exactly how to use your tool without ever having to read your source code.
that's incredibly professional. Which kind of brings up a recurring theme in everything we've discussed today. Whether it was looking up the exact signature of the print function, or figuring out the syntax for the typing module, or learning how to configure argparse, the ultimate answer is always found in the official Python documentation.
The official docs are the definitive source of truth, and knowing how to actually navigate them is arguably the most important meta skill a developer can cultivate.
Because you aren't supposed to memorize all of this, right? The standard library is just far too
Way
vast.
too fast.
And the documentation is split into sections for a reason, right? Like, there's the tutorial for when you are just learning a new concept. Then there's the library reference for when you need the exact technical specifications of a module, like argparse.
Right.
And then there are the how-to guides for when you need a broader overview of paradigms, like functional programming.
Exactly. A beginner tries to memorize syntax. An expert focuses on understanding paradigms, knowing what is possible, and then simply looking up the precise implementation details in the documentation when they actually need them.
That makes so much sense. Well, we have covered a massive amount of ground today. We took a journey from the basics into the absolute realm of the pros.
We really did.
We started with the magic of unpacking, learning how Python routes arguments instantly with stars. We debated the trade-offs of dynamic typing and saw how MyPy brings architectural safety to large code bases.
We completely flipped our mental model of loops, too, moving from imperative micromanagement to declarative comprehensions.
Yeah, that restaurant analogy. And we tackled the absolute limits of hardware memory by streaming data with generators and the yield keyword.
And finally, we wrapped it all up into a polished professional utility using argparse. It really highlights that the leap from a functioning script to professional software isn't just about knowing more commands.
No.
It's about a fundamental shift in mindset.
Right. It is the shift from writing for the machine to writing for the ecosystem.
Spot on.
And that leads me to a final thought I want to leave you, the listener, with today. The foundation of programming, the whole reason you learn loops and variables in the first place, is ultimately about making the computer understand you.
Right.
But the et cetera of Python, the rigorous docstrings, the strict type hints, the beautifully readable comprehensions, these tools aren't really for the computer at all. The machine doesn't care if your code is elegant.
It really doesn't.
These tools are entirely about making your code understandable to the next human who has to read it. So when you open your IDE tomorrow, which of these tools will you implement first to translate your code from merely functional to truly fluent?
A crucial question for any developer looking to level up.
Absolutely. Keep exploring, keep reading those docs, and we'll catch you on the next deep dive.